Today is similar to yesterday. The one thing we're adding is now we're going to take a look at oblique asymptotes. And it's not actually that much trickier, but it is different. But the process or the idea is the same. We need to find the equation of the asymptote. That's what we were doing prior. We were finding the equations of the vertical asymptotes. When do they occur? See, this is the kind of stuff you want to know so well that you can answer that question quickly. When do they occur? Anything that'll make the denominator 0. So we tend to factor the denominator to look at what would make it 0. And then horizontal asymptotes, when do they occur? It's the whole coefficient thing. Sometimes there is one, sometimes it's 0, sometimes there isn't. And that's what we'll see today. If there's an oblique asymptote, there is not a horizontal asymptote. And so, how to find the equation of the asymptotes. And then we can use the equation and the idea of the type of asymptote to do the testing of the behavior around those asymptotes so that we know where the function is going, what it looks like, what it's behaving like. So it's the same thing for oblique asymptotes in general. We need to find the equation of the asymptote. And then we're going to do a test. Our test is going to look a little bit different because it's not going to approach from the left or from the right. It will approach from above or from below, but because it's on an angle, it's in a different way. Right? An oblique asymptote is an asymptote that's on an angle. It's a slanted asymptote. So it's not approaching one single value of y. Like, think about the test we used for horizontal. If it's approaching 3, we put in a really big number, and if it's just below 3, we know it's below. But if it's slanted, and I put in some really big number, that wouldn't tell me if it's just above or just below the asymptote, because I don't know where the asymptote is at that point. You could actually do it that way. That's not how we're going to do it, but you could actually do it that way. In fact, I guess the way we're going to do it, if you don't like it, this would be a way to do it. You could put 1,000 in to the equation of the asymptote, figure out where it is, and then put 1,000 into your function and see if that point is just below or just above. That would tell you the behavior. That's not quite how we're going to do it. This is a bit of a quicker way, I suppose. Okay, so one thing that we want to know is we need to recognize when we have an asymptote, an oblique asymptote. Okay, because if you start hunting for a horizontal asymptote or doing a sketch of a function that has one, but you don't know it has one, things are not going to work out very well. And or vice versa, if you're somehow trying to draw an oblique asymptote and it doesn't have one or something like that, it's going to be like not work out. It's going to confuse you and that sort of thing. So the first thing you need to know is you need to identify whether it has one so you know what type of a graph you're moving towards. But our first example, we're not going to sketch. We are just going to find the oblique asymptote, test around it, and then we'll do a sketch example after. Because we need to know how to find the equation of the oblique asymptote. Okay? So here we go. Let's get to it. Step 1. Find the equation. So what I do notice when I look at this function, oops, I zoomed in too far, is the degree on top is 2. And the degree on the bottom is 1. Whoops, degree. 2 is exactly 1 more than 1. Therefore, there is an oblique asymptote. That's the test. If the degree on top is higher, it's one thing. If the degrees are equal, it's another thing. If the degree on bottom is higher, it's a different thing. It tells us a different thing. If I went into a test and I wasn't fairly confident with which one means which, yikes, like it's really going to slow you down. Those are the little things that, as mucky as it might be to work through that thinking, because it's not intuitive, it's not obvious. I know, I get that. But as mucky as that might be, I think it's really worthwhile. That sort of thing doesn't slow you down, because, you know, then these are going to take forever on a test, and you're not going to get through it. Okay, so it has an oblique asymptote, and when we've determined that and we're looking for the equation, we're going to do division. Do you remember synthetic division and long division? I hope so. It wasn't that long ago. In this case, because I'm dividing by a linear, I can use synthetic, so let's do that. But in some cases, we're going to have to do long division even. One last thing that I was going to say, if the degree between the two was more, so if I had degree 3 on top and degree 1 on bottom, we are not going to graph those. It would have a different kind of strange asymptote. The asymptote actually would look like the degree of the polynomial function that is the difference between the two. Does that make sense? So if it was like a 3 and a 1, the difference is 2, then the asymptote would look like a parabola. If the difference was 3, the asymptote would look like some kind of cubic function. Now, cubic functions get complicated, so exactly what kind, I don't know. But so we don't do that. Okay, we're only doing slant asymptotes. But that's what would happen. All right, so 3, 2, and -4. Again, don't forget the idea of the ghost terms. If you're missing a term, you need to add a 0 in. And we've got to remember how to do this. So bring the 3 down, multiply, subtract, multiply, subtract. -4 minus -8 is 4. And that's my remainder. Don't forget about that. That's really important for what we're doing here. Should we get a remainder? Absolutely. If you didn't, that would tell us something really important. That would actually tell us we're going down the wrong track. We're doing something sort of wrong. Okay? If you didn't get a remainder, then you stop in your tracks and you do something else. But I'm going to let you think about that. I'm not just going to tell you what the answer to that is, because it would be a really interesting thing. All the stuff we've done about all the different properties of rational functions, that would be a connection you could make on your own. What would happen if the remainder is 0? What would that mean? I'll give you the one hint, is what does it mean for something to be a factor and divides evenly into something? Like it means a remainder of 0, right? But what does that mean in terms of the other stuff we've done in this unit? Anyway, but you will expect to get remainders in this case. So that means, what did we just do here? I have enough room to write this. That means the function on top, which is 3x squared plus 2x minus 4. Yep. Oh, I thought you were going to ask a question. Very good. That's exactly what I wanted you to do. What did you say? 3x? Okay, so if you want to just watch, there's your 3x minus 4, right? Remember, that's the quotient. That's the divisor. So the dividend, all we did, like, yes, we started with this function, but we took the top part and divided it by the bottom part. So we took the dividend, divided it by the divisor. This is our result, quotient, that's our remainder. And this is our what we called our division statement. Do you remember writing that a while ago? So there was good reason. Look at this squirrel peeking at, look at this guy. He's like looking at you. What was I saying? So that means the function here, this is another way of writing it. Those two things plus what's left. And we did a little thing where we did that with real numbers, like what's 22 divided by 5? 5 times 4 plus 2, right? You could rewrite it that way. Okay. And what that means is my original function, f at x, equals this. X plus 2 times 3x minus 4 plus 4. That's a way of rewriting the top of the original function over x plus 2, right? That was f at x. Take a look at our original question. That's what it was. We okay with that? So all that work was to rewrite the top. Now, when I actually do this division, I hope we know that this was a little trick we used in the trigonometry unit, where I can rewrite this that way. I can actually split it like, so think about adding fractions, common denominator, you add the tops. I've just done that the opposite way. You don't need to like worry about identities or anything for this. It's the same every time. You don't have to show both those steps. But what I see in the left part is those guys will divide to 1. And so I can basically rewrite my function like this. And this is how you calculate the equation of the oblique asymptote. Okay, that's the process. We don't know what it is. Some of you might have guessed what it is. We don't know what it is yet, but I'm going to show you one thing. Put your pencil down and watch. I want you to watch something. This is good for our thinking. Hey, stop it. What happens to this when x gets really, 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 really big, positive or negative? Don't sit there and wait for somebody else to do it. Challenge yourself. Think about it. How do we know the behavior of something? Where is x in this? You make it really big. What happens? Emily? Yes, if that was the only part of it. Yeah, what you're saying is like that, but because the x-axis is what value of y? What do you think? What were you going to say? Oh, you didn't? Oh. I thought, in my peripheral, I thought you did. Jason, you did? What were you going to say?
I was just going to say, if x was positive, it was really big, it would be a really small number. If x was negative, it was really big, it would be a really small negative number.
Negative number. Good. Which is what, Emily, you were saying, like, it gets close to 0, right? The x-axis is like your 0, so it's getting really close to 0. If x is really, really big, that makes the denominator really, 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 really big, which makes the whole thing really, 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 really small. So what does that mean? That means the function, when I go out really far to the right or to the left, I put f at 1,000 in. What does that mean? Again, these are simple ideas, but this forces us to really think about what it means. F at 1,000. So think about the xy graph. If I put x equals 1,000 in, I'm going way out the graph, way out to the right. Way out to the right on the graph. If I put negative 1,000, I'm going way out. Where is my function when I go way out to the left? So it's going to be basically this plus or minus, depending on the sign, a tiny, 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 tiny little bit. Basically nothing. Otherwise, it'll basically be this. So what is this? This is our oblique asymptote. This is the line that as x gets bigger, this whole thing is our function still. We've rewritten it in an awkward way. That's not useful for sketching except for the oblique asymptote. So our function is basically this, plus or minus a tiny, tiny, tiny little bit when x gets big or x gets small. And is it directly above that or directly below that? Well, that's what we're going to find out. Otherwise, it's basically that line. So our function will be just above it or just below it. That's what an asymptote is. But otherwise, it's that line. So, basically, 0 when x is really big or small, like negative. Really big plus minus. And then this is our oblique asymptote. Any questions? So a little bit of details about our oblique asymptote. Its equation is 3x minus 4. What is important about a straight line? Please, please, please don't let this be what stops you from being able to sketch a grade 9 skill graphing lines. The problem is you haven't done a lot of it. And then it comes up once or twice in this course and you just skip those questions like, I don't really want to relearn that right now. I could do it if I wanted to, but I don't really want to bother with it right now. And then the test comes up and you have to be able to do it and you realize you actually kind of forget how to graph a line and it takes you 10 minutes or something like that, right? So you got to go back and do it. But slope is 3. Did I teach any of you in grade 9? I don't think so. What's the one thing that's important about slope that will actually let you answer almost any other question about slope that you ever have to? The one kind of thing you can remember. Right is a fraction. What is that fraction? Rise over run. This is what I do to my grade 9. Rise over run. 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 Say it 1,000 times in your head. Rise over run. So just remember that about slope. Okay, y-intercept is -4. This is not something you do in grade 9, but it's something that's easy for us now. X-intercept. So you plug in 0 for y. We've done this 1,000 times. All of that's important because we want to know like where it is relative to other asymptotes and that sort of thing, okay? For some kind of a reasonably accurate sketch. Everybody okay with that? Okay, so now we're going to look at the end behaviors or the behaviors around the asymptote. And I'm just going to remind myself that the remainder is 4 over x plus 2. That's what we're going to use. So when x is 1,000, whoops, that's 100, 1,000, our remainder is 4 over 1,000 plus 2, which is obviously, you don't have to show all these steps, but just for clarity for us, which is 4 over 1,002, which is, who cares, but positive. Okay? When x is -1,000, it might look like whenever we put in a positive, we're going to get positive, and whenever we put in negative, we're going to get negative, but it's not the case, so we can't just assume that. Our remainder is 4 over -1,000 plus 2, which is 4 over -9,998. That's 10,000, sorry, that's not right. Too many 9s. There we go. Not that it really matters because in the end, it's going to be negative, obviously. Again, that's like math you can kind of do in your head, right? You can do that in your head. You don't really have to show any of that. But it's the remainder that's positive, not the y values. It's the remainder that's positive or negative that we care about. So you should say x equals 1,000. Remainder is positive. Remainder is negative. Okay? In fact, yeah, that's good. We good? Okay. So if it's positive, if it's greater than 0, therefore, we're above the graph because the remainder tells us where we are in relation to that line. So if I'm basically at that line plus a tiny little bit, I'm directly above it. If I'm basically at that line, but I'm I'm minus a little bit, I'm just below. And again, it's slanted off one way or another. It's not a horizontal asymptote, so it's not quite as clear. We okay with that? Last little thing, I'm running out of space. Oh, here we go. I'm just going to sketch my slant asymptote. That's all, my oblique asymptote. Using those properties that we just went over, a quick little grade 9 review. So the y-intercept is -4. The x-intercept is 4/3, which is just over 1. And every 1 that I go over, I go up 3. So it would look like that. And so when it's all the way to the right, if it's just above, it's going to be going something like that. And all the way the other side, when it's just below, it's going to be going something like that, right? And we're going to sketch one now to see what the rest of it would do. Okay? Any questions? You sure? All right, let's do it. So we're going to start from the beginning, doing things in order. What do you notice about this question? Anything? There's no wrong answer here, because knowing where to start and how to move forward has to do with the observations you make about the different parts to it. So however you connect to it, whatever you think about, whatever jumps out at you is important. Megan, what were you going to say? Nice. Difference of cubes on top. I like it. And you said? Which tells us? Which, no kidding, because today's a lesson on oblique asymptotes. But, right, so it's going to have one. The top is a difference of cubes. That's important. That's useful. Anything else about it? It's not quite the same as the... Go ahead. I like that. That's kind of just what I was going to say. Like the bottom is a quadratic, so we can't use synthetic division on that. Don't try. We have to use long division. So yes, you still need to know how to do that. And it's a quadratic in general. So how many vertical asymptotes is it going to have? Like there's all these different things that you could kind of start thinking about. You don't have to think about all of them all at once. And what do we start with when we start sketching? What did we start with yesterday? Our intercepts. So we're going to do the same thing. So 0 cubed minus 1 over 0 squared minus 2 times 0 minus 3. That gives me positive 1/3. That's an easy one again, so you may not have to rewrite it as a decimal, but there it is, 0 point. That's not supposed to look like less than or equal to. I don't know what happened there. Different ways to do the x-intercept in this question. And it all comes down to your skills from the previous unit solving polynomial equations. However you would choose to do it. But I can think of at least 2 ways. And I'm going to choose to do it this way for now. By moving the 1 over. Taking the cube root of both sides. Done. Yep. Would it? You tell me. What? You think that because when we take square roots, it's plus or minus. So then my question would be, is it the same for all roots? Is it the same for cube roots? This is something that people should know. What do you think? Yeah, good. So for all odd exponents, we know the sign, because -1 cubed and 1 cubed don't give us the same thing, right? They give us different answers, so when we take the cube root, we know which one we started with. Think about the opposite operation. Always a helpful thing to do. Whereas with squaring 1 and squaring -1, they both give us, or any number, gives us the same answer. So we don't know which one it is, so it gives us 2. Does that make sense? Good. All right. That's it. So we only have one x-intercept. Is that strange? Not strange. It may happen. You may have 2. You might have 1. But we do only have 1. So let's move on to the asymptotes. Oh my gosh. We'll still start with the vertical asymptotes. And what do we like to do when we're doing the vertical asymptotes? We like to factor everything. So let's go ahead and do that. And while we're at it, just for kicks, I'm going to factor the top. Just because I love factoring so much. That's an easy one. So here's where you could have solved the top by factoring, and some people, I'm sure, did that on the test and would do it that way, and it's a fine way to do it. But what we know from an activity we've done in this class is that this part will not give us a real answer. It never will. It can't. If you're not sure why, you can go back and think about that activity or ask me later, or we'll talk about it again, or you can just take my word for it that when you factor a sum or a difference of cubes, you will only get one real answer. That's why solving it the other way is fine, right? Like solving by isolating is fine because that will only give us one answer, but that's the answer, okay? But again, this part's not real. It won't be real, so there's no x-intercepts there. If you're graphing, we graph in real numbers only. You can graph in what we call the complex plane. We just don't in high school anymore. We used to. Okay, so we're actually doing our vertical asymptotes here. So we've got x equals 3 and x equals -1. And we have to test the behavior around these two, so I'm going to start with x equals 3. Go ahead. Don't just copy what I'm doing. You go ahead and do it yourself. This is the part where now you got to start knowing which test to use for which type. And sure, if you do enough of these, I'm sure you'll memorize it. But if you don't memorize it, then you should just understand it because you can always just figure it out. You can always just think, well, what's happening to x's as I'm getting close to a vertical asymptote? What's the x doing? Not sure what to do. I did get us started up there so you could peek. I put in a number just below 3, just below the value 3, just smaller. So that's going to be, this is a vertical asymptote. It's going to look like this. So something smaller than 3 is going to be just to the left. And I always try to structure my thinking left first, then right. I just think it's good to be consistent because you're going to do all this work and then you have to go back and read it. And when you're reading it, if you've done it the same way every time, you'll kind of know which one is which. And it'll just save you a bit of time and a bit of thinking. You can think about the harder parts. Just good habit. Okay, so we're just to the left of this. And here's what I like to do again, if you want to watch. 2.99999 minus 1 will be positive. If I take a positive number, I square it, I add it, and I add another positive number, I don't care what that actually is. It's going to be positive, right? It has to be positive. There is a case where this will be negative, and if you're not sure, if you can't figure out what that is, then you're going to have to plug it into your calculator, but you could plug just that part into your calculator. But it's probably something most of us could figure out if we thought about it. Okay, so 2.99 minus 3, well, that's going to be negative because the minus 3 is bigger. And that's positive, positive, negative, and positive. So we've got one negative out of 4. So this one's going to be negative. And then what am I going to put here? 3.001. And 3.001 will give me those 3 same positives, and the other one will also be positive because now what I'm looking at is bigger than that. Like that's the one that was negative, but now the positive is a little bit bigger because I just crossed over that one. So now it's going to be positive. Save some room, I guess I'll work down here. X equals, what was the other one? Negative 1. There it is. So what values do we want to do? Again, this is a vertical asymptote. We want to get really, really close to -1, but just to the left of it and just to the right. So just to the left would now look like that, and just to the right would look like that. And I can do the same thing for the first one. That's going to be negative. This is harder, but this is going to be positive. That's going to be negative, and that's going to be positive. So I got 2 negatives. Wait, did I do that right? Didn't do that right. That one's going to be negative. That one's going to be negative. This one's going to be negative as well, sorry. So I get 3 negatives and 1 positive. And again, if you can't figure out why this one is negative, that's the type, when it's close to 1, I would say you could punch in your calculator. Every question is different, so in some cases you may need to. But for this one, just because they're all positive, it's not so bad. Okay, so this one's going to be negative because I had 3 negatives. Tell me if I'm wrong. If anybody punched this into the calculator, tell me if I make a mistake here. And then the next one is going to be very similar. This is still negative. This is still positive. This is still negative, but now this one's positive because the +1 is bigger than that. So now I get a positive. Yep. Yes. So you check it on your calculator if you're not sure. But in my head, here's the way I think about it. I'm going to take a number and square it. That's going to be positive. And then I'm adding 1. And I'm subtracting that small number. That small number is less than 1. So the small number less than 1 plus 1, that's going to be positive, plus a little bit more positive, like it's going to be positive. But that's kind of, like, again, it's messy thinking. So I in that case, if that's not something that you can kind of do naturally, you may want to punch it into your calculator. It's a fine way to do it. Yep.
How I did it was that I took the original function, and then I used the original function to the top, and then I used the factor function to the bottom.
That's a great idea. Think about, Use what you have. Use all your resources. That's a way better idea. Is thinking about the original function. Because when I take 0.999 and cube it, it's still going to be negative, but I know the kind of negative is going to be, yeah, very good. Okay. So now we didn't do any conclusions, so let's do our conclusions. This is as x approaches 3 from the left, y is going to negative infinity. And as x approaches 3 from the right, these are vertical asymptotes, right? Y is going to positive infinity. As x approaches negative 1 from the left, y goes, to negative infinity. And as x approaches negative 1 from the right, y goes to positive infinity. You may choose to write those conclusions as you go. I didn't leave them to the end on purpose, but either way. Be okay with that? Do that for a few days. Hopefully that's getting more and more kind of familiar and common. Okay, let's continue. We already talked about this. It has an oblique asymptote, which means it does not have a horizontal asymptote. Okay? So we don't have to worry about horizontal asymptotes. We have to do the oblique asymptote. And we already talked about this. We can't use synthetic division. The first step is to find the equation of the oblique asymptote. We can't use synthetic because what we're dividing by is a quadratic. So we have to use long division. So we're going to do that. X squared minus 2x minus 3. And it's x cubed minus 1. So it's x cubed plus 0x squared plus 0x minus 1. That's what I was talking about with ghost terms. You got to watch for those. X squared goes into x cubed. X times. Because x times x squared gives me x cubed. You might want to watch if you want a quick sort of view of how to do this. Then I take this and I multiply by each of these three one at a time and put my answer here, right? So x times negative 2x is negative 2x squared. X times negative 3 is negative 3x. So then I subtract. X cubed minus x cubed is 0. That has to happen. We set it up that way. 0 minus negative 2 is 2. 0 minus negative 3 is 3. Bring down the minus 1. And rinse and repeat. X squared goes into 2x squared, positive 2 times. So I get 2x squared. 2 times negative 2 is negative 4x. 2 times negative 3 is negative 6. And I subtract, and I get 0 here. That has to happen. And I get 3 minus negative 4 is positive 7. And 1 minus negative 6 is negative 1 plus 6, which is negative 5. Positive 5. All right? Everybody okay with that? That means x cubed minus 1 equals we're going to start with the dividend. You don't have to. You have to write this step, but you don't have to start with the dividend, but we're going to. to keep it consistent with what we did before. You don't want to get confused because in this case, our result was linear. The x plus 2 was what we ended up with. You don't want to get confused about which one you're keeping and which one's going away, right? So plus 7x plus 5, which means f at x equals that whole thing remember, this is what we're dividing by. That was what was in the original question. The remainder part looks quite different from the last time, but that doesn't really matter much. What matters is that you get it exactly right. Like, we can't ignore exactly what the remainder part is because that's what's going to determine whether we're just above or just below the slant asymptote. So we have to have it set up right. But it does look quite different, but that's fine. It's going to. So these guys are gone, and we get x plus 2, there's our asymptote, plus 7x plus 5 over x squared minus 2x minus 3. This is an interesting thing to think about. And in fact, I remember doing this in university and it was really weird, but there's an easy side to it. And I wish I guess that my professors had, and maybe they did, and I don't know, zoned out and wasn't listening or something at that time, like we all do, but that they had explained it this way, like, so if I look at the top and the bottom, when I put a big value of x in, well, I'm going to have that big value of x on top as well. The last one was 4 over. So when I put 1,000 in, the bottom gets really big. So the whole thing gets really small. But it's not quite as simple when I've got an x on top as well. But when I put a big number in for x and then square it, that's going to get bigger than just that number. So over time, the bottom is still going to get way bigger than the top. Don't you agree? And so that has to do with the degree on top and the degree on bottom. See how important degree is? Grade 9, you start learning it, you don't know anything about it. Now all of a sudden you realize, like, man, this is a big deal. And so that's how we can still see that putting a big value in will make it really big or really small kind of thing. Okay? Okay. Let's, we have everything we need, I think. Oh, behaviors around this asymptote. So we do the same thing. X equals 100. Again, you may want to use your calculator. The bottom part is factorable, so you could still think about it that way. We've already factored it from before. That might be easy, because this is going to be 700 plus 5. That's obviously positive. The bottom is also going to be positive. So our remainder is going to be greater than 0 or positive. Therefore, it's above. And when I put in negative 100, I'm going to get negative 795 on top. And if I think about This is going to be negative 100, so I'm looking up here at the factored form. Both of those bottom brackets will be negative as well. So I have 3 negatives overall, right? So in this case, the remainder is definitely less than 0 or negative. Therefore, it's below. Questions? We got all the details we need. Now we can sketch. My vertical asymptotes are 3 and negative 1. I have an x-intercept at positive 1 and a y-intercept at positive 0.3. Oh, the one thing that I forgot to do, sorry. We'll just do it right here. For our oblique asymptote, where do I have space? I'll do it here. So y equals x plus 2. Maybe it's not as important, but I think this is a good thing to do. The y-intercept is negative 2, and the x-intercept is negative 2. Sorry, the y-intercept is positive 2, obviously. The x-intercept is negative 2. That's of the oblique asymptote. So plus 2 is going to be right around up here. And negative 2 is going to be right around here. I better use my ruler for this one. Uh-oh. Okay, and again, if you want to watch, I'm going to start running through this. So let's take a look at my first vertical asymptote there. As x approaches 3 from the left, it goes to negative infinity. So that's going to be down here. As x approaches 3 from the right, it was positive infinity. So that's going to be up here to the right. As x approaches negative 1 from the left, I go to negative infinity. As x approaches negative 1 from the right, I go to positive infinity. So now I know what the middle part's going to look like. It comes down, does this funny bloop, and goes like that. Because it was approaching 1 from the left and 1 from the right, so that's how I determine that. And the intercepts as well confirm all that. It all fits. If you made a mistake somewhere along the way, something wouldn't fit. You'd be trying to draw a graph, and it would either cross where you never calculated an x-intercept, or it wouldn't cross where there was one or something, right? One or the other, I guess. And then, my oblique asymptote here, when I went far out to the right, positive 100, I was above. Hello? Uh-oh. So I'm going to be over here somewhere. So this is going to go like this. And if you remember, we did look at a couple of these. That's kind of what they look like, right? And then the other one, I'm below. So I'm here below it, which again, fits. Very nice. Any questions? We're going to do another day on this on Monday, so there'll be more chance to practice. But then Tuesday, we move into something a little bit different. So by the end of the day, Monday, You want to be an expert at sketching all the different kinds, including oblique asymptotes. Because then we're moving on. There's a chance that our test will fall on Friday of next week.